So this is part 2 of experiment 6 video, and this is the combinatorial synthesis of azo dyes. So the topic that I wanted to talk about um, in part 2 is this idea of how is it that organic molecules absorb light. And so let me just start the slideshow. So how is it that organic molecules can absorb light, and is there anything that we can um, glean from structure to infer whether it will absorb light? So if you think back to your general chemistry days, the whole premise of a molecule absorbing a photon of light is that when you absorb a photon of light, so light is going to absorb into the system, you're going to promote an electron from its ground state to some excited state that's shown here. And so if you're dealing with in the general chemistry world and you're dealing with inorganic molecules, that could be an electron going from a ground state bonding orbital to a different vibrational state. Typically in organic molecules, we're going to be talking about transitions from pi bonding orbitals to pi star antibonding orbitals, and I'll talk about that in a little bit more detail here. So what can we understand about the structure of a molecule and how that correlates to whether it's going to absorb light? And to that extent, can we then understand something about the wavelengths of light that are going to be absorbed? Because really, I mean, we're going to be interested in anything that's going to be above 280 to 300 nanometers, right? Because that's going to get us into the visible range, anywhere from 800 to 300. So if we think about the molecular orbital system of just ethylene, so let me switch my pointer here. So if we think about the molecular orbital system of ethylene, we're going to have two pi orbitals, right? We're going to have a pi star antibonding orbital, and then we're going to have a pi bonding orbital. If we then take this one step further and look at a system like butadiene, it's going to be a little bit more complicated. So if you'll remember, if you have um, four atoms that are going to contribute to your pi system, then you're going to have 4 pi molecular orbitals. And so you're going to have 2 antibonding molecular orbitals, and then 2 bonding molecular orbitals. And so we'll just call these pi 1, pi 2, pi 3, pi 4. And then so you have four total electrons in this system. And what you're going to notice that's so different about the system of ethylene and then comparing that to butadiene, it's going to be the energy that is needed to promote an electron from your pi bonding orbital up into the pi star antibonding orbital. So you're going to have a difference in energy here, and then you're going to have a difference in energy here. And that hopefully what you can see is that the difference in energy in the butadiene system is much smaller than the difference of energy in the ethylene system. And that manifests itself by the wavelength of light that is needed to promote an electron from the pi bonding to the pi star antibonding. That as you go to longer and longer conjugation, that you have a smaller and smaller energy gap between what's referred to as the highest occupied molecular orbital and then the lowest unoccupied molecular orbital. So between the HOMO and then the LUMO. And as you extend the conjugation from two pi bonds to 3 pi bonds to multiple pi bonds, that difference in energy is going to keep going down, and that's going to keep manifesting itself as the wavelength is going to keep migrating from the far UV up until you hit somewhere right around here, and that's going to be right around the visible. And then once you get past that, the more conjugation that you add into it, the closer you're going to be to red. You might hear in the background my 2-year-old daughter is helping her best to contribute to this lecture. So this examples of long conjugation are important in a variety of biological molecules. The one that you may be most familiar with is beta-carotene. And so when we think about beta-carotene is the major precursor molecule to vitamin A. So what happens is that you get cleavage at this point into two symmetrical molecules, and then once you have cleavage of those two symmetrical molecules, those get converted into vitamin A. Vitamin A is then conjugated to a protein called rhodopsin, and that's what's responsible for our ability to see things. Lycopene is the molecule that's responsible for the red color in tomatoes, and most of you should be familiar with indigo, which is the first example of a naturally occurring molecule that was later synthesized for the specific purpose of developing dyes for clothing. Okay, and so that will be the end of lecture 2, or part 2 of this experiment, or part 2 of this lecture, and so the final part 3, we'll talk about the chemistry.